In this tutorial, we're going to talk about some of the particularities of the stress-strain analysis when we're working with the North American design codes. We're going to focus on the things that make a significant difference. What we don't mention here are things that are practically the same or exactly the same in other design codes. So we're also going to focus a bit more on the components, specifically on the bolts, welds, anchors and concrete, and the shear strength when it refers to base shear and frictional resistance. So we're going to start with the bolts, where basically, and this applies to practically all the components, one of the most noticeable differences is the nomenclature itself. The nomenclature is one of the biggest differences, as each code has different systems for naming things. A particularity of the North American code, which sets it apart from the Eurocode, is the bearing check. We can see that the table is very similar to what we saw in Eurocode, but with the difference that now we have this bearing strength. Whilst it's true that we have something similar in Eurocode, in the American code this result comes from the smallest value of two limit states. So it's the smaller of, on the one hand, the term that represents the tear out, and on the other hand, the term that represents the bearing of the plate. Both are limit states. They are similar, both are related to the shear in the bolts, but each one has a different strength. So the software shows us the smaller of these two. And obviously, the calculation is very similar to what was seen in the European standards. The software automatically obtains a distance, etc. So, continuing from here, the rest is exactly the same. UTT, UTS, UTTS, which are the factors of utilization, percentages of utilization in tension, shear, and interaction. Here we have the table with the results of the bolt's tensile strength and shear strength, and we see that it's very similar in this aspect. Now, if we look at preloaded bolts, which are basically joints or slip critical connections, as they're known in the AISC code, it's assumed that they are bolts that have a preload indicated, and consequently, we want these connections to resist the shear through friction. This check is done via each one of the bolts. The check is very similar to that done in Eurocode, but with the difference that we see that the pre-tension load does not appear here in this table. This is because the American code only allows us to work with 70% of the fastener's failure resistance as the pre-tension load. We can't use different pre-tension factors. So we're just going to have the factors that are given in the tables by the standards. In the same way, we could change the slip coefficient mu depending on the surface that we have. This is done, as we saw before, in the code setup. We can change this 0.30 to another value. Now, moving on, one of the components where there are more differences is the weld, the fillet weld specifically. The same as in Eurocode, the full penetration weld isn't checked. Now, if we go to the welds, we'll use the equivalent stresses to help us visualize it. What we have here is a table that's very similar to what we've seen before, but with a few differences that we'll look at. Some columns are the same. We have the status column, the item column, which refers to the plate that we're welding, the edge of the plate on which the weld will be done, the electrode, that's important, and then the differences start appearing. The first is the throat thickness of the weld. In the European code, this is considered the size of the weld, but in the American code, the size of the weld is considered the length of one of the sides of the triangle, as opposed to the effective throat thickness being considered the height of the triangle. So it's a bit different. Normally, the American code is specified here, and when we specify the weld size in the software, we're specifying the LS. We're going to see some other differences. Here we have the weld fillet length, for example, for these welds here. For example, for this one. We see that we have the chord length, but we also have a length called LC. What is this length? It's the length of the critical element. As we can see, this weld is divided into various segments. we can see that we have the various finite elements, in this case 4. What does the software do? It evaluates the welds in each one of these segments, each of these finite elements, and it shows us the result of the most critical element. Remember that the weld in IDEA is modelled with plate elements. If we put it into the side view, we see that they are extended plates in which the thickness that we don't see in this direction will be the throat thickness, which is the TH. Next, we've got the load cases, and then it shows us the resultant force, i.e. the force in the critical element. This force is obtained via the finite element analysis, and it's accompanied by something quite interesting, which is the angle that forms between the axial axis of the weld cord and the direction of the force. Why is this angle important? If we look at the equation, we realize that the weld strength depends on the angle of application of the force. Why is this? Well, there are many studies that have proved that welds loaded longitudinally have less strength than welds that are loaded in a perpendicular manner. Obviously, sacrificing a bit of ductility or a bit of deformation on the way, but this is basically the reason why this angle is taken into account. As the software automatically obtains this force via the integration of the main stresses, we can obtain this angle, and with this we can calculate this weld strength value. So we see that this type of weld resists this, and multiplying by the area, we obtain the reduced resistance, which must be greater than the Fn, which is the resultant force that comes from the finite element analysis. So this is how it would be checked in the software, obtaining this utilization factor, which will obviously depend on these two values, as we can see here. We can see in the graphics, in the same way as in the other codes, how the stresses vary in each of the finite elements, how the equivalent stresses vary. So we can see which is under the most demand. For example, for this fillet here, we can quickly see, it's even shown by the colors, that this element here is the one that's most loaded. Probably, this will be the element that governs the design. It will be the critical element, as we saw in this example. In other things, there are small differences, for example, relating to the anchors. The way of working is fairly similar, with the difference that there are these limits that are a bit different. The principles are the same, given that the physics stays the same, but the approach may be a little different. So we have the table, as we see here. We're going to change to a general check view, and we can see that we have these anchor bolts, that if we look back at the design, we realize that they've been designed as the mechanism for shear transfer, as we can see here. The shear was transferred directly with the anchors. It's assumed that these bolts are going to absorb all the shear. What do we have here? It's a very similar table. For the load cases, we're seeing each of the forces, in tension and in shear. The shear clearly with its respective direction. If we look at the forces, here we can see the resultant. In this case, it's very obvious because we have a shear in only one direction, and so it's simpler to see where the shear force goes. What else could we have? We could have the limit states related to concrete. Remember that the anchors are embedded in the concrete, and consequently, the concrete also needs to resist these tensile and shear forces, so that the foundation, or the base plate, remains standing. So the first thing is the breakout resistance of the concrete cone. We've already seen this check in Eurocode, where, it's important to mention, these anchors can work in a group. It can be an isolated check of just one anchor, or these anchors can work in a group of anchors, as in this case, because they all have the same strength. Why is this? Because all these anchors are working as a group of anchors in tension. What does this depend on? It depends on the position of the anchors themselves and on their geometry. If the anchors are fairly close to one another, they work as a group. If they're very spaced out, they work independently. On the other hand, we have the breakout resistance of the anchor, or the slip resistance. Basically, this is a check that only appears when we have anchors with washers on the ends. This is because if we have smooth anchors, it's assumed that they are mechanic anchors, special anchors with epoxy resin, or another type of chemical preparation. In these cases, it's assumed that the manufacturer guarantees us this adherence, or gives us a specific resistance, and for this reason, the check does not automatically appear in the software. The other resistance that we have is lateral pry-out strength, which also depends on the positioning of the anchors in relation to the edge. Basically, as we can see here, they form a sort of pry-out in this zone, which doesn't affect the tensile strength of the anchor. Continuing along here, we have the shear resistance to shear breakout, similar to tension but with shear, and concrete pry-out resistance. This is also a strength that's quite interesting and that depends on the tensile cone breakout resistance. If there's a lot of resistance to the cone, there's going to be much more pry-out resistance. This is particularly when we have isolated anchors. That's when we might get this type of limit state failure. As we can see, what's done is to obtain the utilization percentage. This is what the software shows us, the most critical, according to each one of these limit states. But what we have in the end is a percentage of tension, a percentage of shear, and a percentage of tension and shear interaction. We can review the report with no difficulty, as we've seen in the other examples. We can see each one of the factors that were obtained from the standard, and that refer specifically to the provisions of the standard that we're using. We can see that it tells us, for example, about the concrete breakout resistance of the anchors in tension, or about the cone resistance, where it says that the check is done for a common group of anchors in tension, and we see which ones they are. It's A2, A3, A4, A5, and A6 for this example. The same with the other limit states. Now we're going to see the concrete bearing on the concrete block, as it's known in the software, which is also fairly interesting. We can see that in this zone, this concrete is compressing, and consequently we're going to have an area which is in contact with the concrete. So if we look here, we see what's happening. We've got two areas. One is the area that we have here, which is in contact with the concrete, and we have an area that is geometrically similar, which will be this one, area number 2. We've got area number 1, which we see here, and area number 2, which is this complete area, and the one that, let's say, provides the resistance. According to these two areas, we obtain the average stress, which is our acting force, and we're going to calculate the concrete resistance. We're going to see the equation here. It's a very short equation. We see that, basically, the resistance depends on these two areas, and we can see that this resistance is bounded by a maximum value. And we're going to obtain a stress, which is what the concrete resists, and which must be greater than the acting stress. Now, if the shear force transfer mechanism is not via the anchors, instead is via friction, we see that it's a bit different. The shear tab appears, as we've seen before. The only interesting difference, in terms of the European standard, is that the software straight away works with a resultant force. The shear resistance is calculated, as we see here. We have the acting force, and it's calculated as shear resistance due to friction, which is a very similar calculation, but the software doesn't work with the shears separately. Instead, it works with the resultant of the shear. This mu coefficient can be changed in a similar way to how it's done in the other codes. As we see here, this coefficient is 0.4. Lastly, we'll look at the shear lug. One of the interesting details is that, in this case, we've used a cross shear lug, which is fairly typical. The software checks the lug using finite elements, using the same criteria that's used for the other plates, given that the lug is modelled explicitly. The welds of this lug are also modelled. Consequently, what we need is for it to satisfy checks via the plastic deformation criteria that we've already used for other elements. Now, what we're not modelling in the software, what we're not modelling explicitly as a solid, but rather via springs and simplifications, is the concrete. The concrete is not modelled directly, and consequently the concrete checks, as we've seen, are analytical. The same is true for the shear lugs. We have, we could say, two principal resistances, a concrete block resistance and a concrete cone resistance. This resistance that we had initially is a resistance associated with the bearing of the lug on the concrete, and the other is a resistance to the shear failure of the lug. So basically, it's these two limit states. We see that we can check the analysis report without any difficulty, as we've done with the other components. We have the two main checks, the bearing strength and the shear breakout resistance, which obviously depend on some geometric considerations and on the shear lug itself. And here we can finish this video tutorial.